Okay, everybody, here we go with the second part of the video notes for section 8.1. And now we're actually going to begin the geometry right here. So we begin now with theorem 8.1, the first theorem presented to us in chapter 8, and what is without question the most famous and well-known theorem in all of geometry, that being the Pythagorean theorem. So most theorems are written in if-then form. This one, the way I have it written right here, is not written in that form, but we could if we wanted to. So what does it say? The Pythagorean theorem tells us something that in words maybe doesn't make a whole lot of sense, that the sum of the squares of the legs of a right triangle is equal to the square of its hypotenuse. Now that's one, when I say that to a lot of people and say, all right, does everybody get it? They all kind of look at me blankly. So let's take a look at what this is in symbols right here, guys, as we look at it again. All right, going back to the words now, the sum of the squares of the legs of a right triangle. Little bit of a vocab review before we go any further. In every right triangle, you have one right angle, which we have located in the bottom left-hand corner here. The two sides that meet to form this right angle right here are called the legs of your triangle. So A is a leg and B is a leg. And the third side of your right triangle, the one that's located across from your right angle, that is called the hypotenuse of the right triangle. You want to be careful about how you define it. A lot of people tell me when I ask them what a hypotenuse is, they tell me that a hypotenuse is the longest side in a right triangle. They're correct, but that's actually a property, and we'll talk about that a little bit later in this chapter of a hypotenuse, but the actual definition deals with its location. The hypotenuse is located opposite from the right angle. Okay, so back to the wording here of this theorem. It says that the sum, which tells us we're going to be doing some adding, of the squares, which means we're going to be doing some squaring, of the legs of a right triangle. So we're going to take one of our legs and square it. That's where we get this leg squared from, plus the other leg here, and we square that. So that right there, this expression from here to here, is the sum of the squares of the legs of a right triangle. Is equal to is an important phrase. That is always where we stop and put the equal sign in our equation here. And then equal to what? The square of its hypotenuse. So here's the length of the hypotenuse, and we square that as well. Now, what most people know, and I think you guys know this because this is probably the way it was taught to you in middle school whenever you learned it, is this version of the formula, which admittedly is much easier to memorize than anything that's either verbal right here or somewhat symbolic right here. Most everybody in the world prefers this version of the formula here. A squared plus B squared is equal to C squared, and that's perfectly fine to use as long as we understand that A is the length of a leg, that B is the length of a leg, and that C always has to represent the length of your hypotenuse. If you get that mixed up, the Pythagorean theorem is not going to work. So I'm actually a fan of doing it this way. Leg squared plus leg squared equals hypotenuse squared, because I think if you can force yourself to be a little bit disciplined in that regard, you're going to make fewer mistakes. But an awful lot of people have done A squared plus B squared equals C squared, and they have survived. Pretty sure no one's died just yet. So, what the Pythagorean theorem is really useful for is allowing us to take a right triangle where two sides are known and to figure out the length of the third side, and that's what we're going to do right here. The first thing you want to notice, this triangle has a corner mark right there, which makes it a right triangle. The Pythagorean theorem only applies to right triangles. If this triangle looked something like this, where this was a 14 and this was a 48 and this was an x, the Pythagorean theorem would not apply to this figure because this is not a right triangle. But in the one that is given to us, we're good to go. Okay, so I'm going to do this the way I like to do it. I always like to begin here by writing leg squared plus leg squared is equal to hypotenuse squared. And now we fill in what we know. So just ask yourself, how long is one of my legs? Well, here's the right angle, so 14 is one of the two legs here. So okay, 14 squared plus. Now we move on to the other leg. Again, here's the right angle, so this is the other leg right here, 48 squared equals, and now ask yourself, how long is the hypotenuse? Well, here's the right angle. We look across from it. X is our hypotenuse. That's our unknown. So this is how we would kind of do step 2. I always like to do problems like this as kind of a 3-step problem format right here. Step 1 is to write out the formula. Step 2 is to fill in what you know. And then step 3, let's evaluate what we can. You can do these two things here separately, but there's no need to. Since they're both on the same side of the equation, I'm going to go ahead and in one step in my calculator, I'm going to type in 14 squared plus 48 squared. You don't need to do them separately. That whole left side is now equal to 2,500. That equals x squared. And now, something that you guys learned last year in Algebra 1, and you'll see next year in Algebra 2 as well. Here's your variable. All right. We have x now being squared. We have to undo that square. So ask yourself the question, how do I undo a square? Well, square root is the inverse operation of a square. So we're going to take the square root of the right side, and then of course we balance that out by taking the square root of the left side. Sorry guys, excuse me just a second. All right, there we go. So we take the square root of both sides, and let's see what now happens. I'm actually going to flip sides on you here. The square root of x squared, get used to this, the square and the square root cancel each other out. So that side really just becomes x. And on the left side, which I'm now going to move to my right, you have the square root of 2,500. That's one you can just put into your calculator. And we're going to cross our fingers and hope that it ends up being a perfect square. And in this case, it is, everybody. X is equal to 50. Now think about that answer for just a second with something we talked about a moment ago. The hypotenuse, as a property now, always needs to be the longest side within a triangle. So we knew, if we thought about it before we even got started, x had to be longer than 48, and this one right here is. All right, so x is equal to 50 is our answer for example A. Let's take a look at what's going on in B. And this one here is a really good example of why I like you guys to do the Pythagorean theorem my way rather than the way that people do it in the past. Don't write this down, everybody, but let me show you the mistake that people tend to make. When people tend to write out a squared plus b squared is equal to c squared, it's very, very easy for them to goof the following up. You will notice that I used c as one of my variables. So naturally, everybody thinks that the c goes right here, and they'll then put a 24 in for A, a 51 in for B, and they'll get C here by itself. Now I'm going to skip a step right here. I'm going to ask you guys to trust me here. We're going to end up then with, let's take a look, 24, 51. We end up then with C is equal to, if we were going to round this, it doesn't work out nicely, 56.36. I'm hoping you guys see the problem with that. The right angle is located right here, which makes 51 the hypotenuse. This needs to be the longest side in the triangle. But what we just found was that C was actually longer. That's something you guys should be on the lookout for. If that happens, we did something wrong, because it's impossible. The hypotenuse has to be the longest side. So that's the mistake. I feel it's a risk there in writing a squared plus b squared equals c squared. So that is the reason that I like you guys to write out leg squared plus leg squared equals hypotenuse squared. I think it slows you down just a little bit and it makes you think. Okay, here we go. How long is one of our legs? Well, here's the right angle, and my legs are going to be the 24 and the C. Doesn't have to be this way, but I always like to put the variable first. So C is not our hypotenuse. It's actually one of our legs. The other leg, right here, that's the 24. So this is C squared plus 24 squared equals, and again, the hypotenuse is always located across from the right angle. It's usually not a bad idea to put a box around that so you see it. So 51 is our hypotenuse, and we're going to square that. Now we're going to go ahead and try to solve this. The first thing we're going to do is simplify these two expressions right here. Since they're on different sides of the equal sign, we have to do them separately. So I'm going to hit 24 squared in my calculator and then hit enter. That's 576 equals the 51 squared should be 2601 over here on the right. Okay, now to get our variable by itself, the first thing we have to do is get rid of that 576, which we'll do by subtracting it from both sides. Minus 576 here and here. Those two cancel, and we end up now with a c squared equals, and 2601 minus 576 is going to get us 2025 for the right-hand side. We undo this square by taking a square root on the left, and we balance that out with a square root on the right. The square and the square root cancel, leaving just a c over there on the left. And the square root of 2025 ends up equaling 45. Now before I box, we should think about this. 51 is our hypotenuse, so really we knew that c had to be less than that 51, and we've got it there, guys, so I feel pretty good about that answer. Okay, moving right along. Okay, now things start to get a little bit more difficult, not in any way that you would notice just by looking at the beginning of this problem here, but I think I see what's happening in this one. Okay, right triangle, two sides are given to us, so we're going to use the Pythagorean theorem. Legs squared plus legs squared is equal to hypotenuse squared. All right, here's your right angle, so your legs are 4 and n, and 16 again is your hypotenuse. So again, I like to put the variable first here. So I'm going to write n squared plus my other leg 4 squared equals our hypotenuse, which is 16 squared. Simplify what you can here. Can't do anything with the n squared. So n squared plus a 16 is equal to 256. Moving right along, we subtract a 16 from both sides, and that, those will cancel, is going to get us n squared equals 240. We have to undo a square, which we do with a square root on the left and a square root on the right. The square and the square root cancel each other out, and we get n equals, and right here we hit a little bit of a thud. If we go to type in, let's try this again, Mr. Fontana, the square root of 240 into our calculator, we can see that 240 is not a perfect square. If you were doing this on a simple calculator, like maybe your phone calculator, you probably got a decimal that I'm going to guess was somewhere in the neighborhood of about 12.2 or 12.3, something like that. We are not looking for decimal answers at this level. So what we need to do is to try to use what we learned in the first section here of 8.1 and try to simplify this radical by finding a perfect square that goes evenly into 240. So what I told you guys to do is to think about that number, your radicand, 240, and cut it in half. That gets us 120. Best case scenario, that number would be a perfect square. But that didn't work here. 120 is not a perfect square. You go down from there. If you go back to your list of red numbers that we did before, the first perfect square smaller than 120 is 100. So you'd want to think about that. Does 100 go evenly into 240? The answer to that is no. Now you can try this in your calculator, but 240 divided by 100 doesn't get you a whole number. Neither does 81. Neither does, I don't think 64 does. Let's try it. 240 divided by 64, which is 8 squared. Nope, that didn't work. 7 squared, 49. Nope, 240 doesn't work dividing by 49. 6 squared, 36. That is not going to work. 5 squared, 25 does not work, but I think we finally get lucky here, guys, when we try to take 240 and divide it by 16. Yep. That one worked out. There's no way to know this with big numbers other than to plug it into your calculator and check. But after some work, I realized that the 240 can be broken up into 16 multiplied by 15. All right, guys. So let's see what we can do now. We break it up into two different square roots. The square root of 16 times the square root of 15, and that one right there can be evaluated. Sorry, I'm kind of out of room here, but the square root of 16, let me go up with this now. The square root of 16 is 4. Nope, not that, is 4, and you can't do anything with the square root of 15, so that just tags along for the ride. And that, everybody, is the value of n written in simple radical form, 4 times the square root of 15. So that was a good bit harder than the ones that we had done before. All right, one last one right here. If we were in class, I would have you guys try this one on your own and see how you do. So feel free to pause the video and give it a shot if you would like. But if not, here we go. Right triangle, two sides are given, so we're going to use the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. Take a second and think now. Here's my right angle, so 7 is a leg, t is a leg, but 14 is the hypotenuse. Okay, so for my first leg, I like to put my variable first there. T squared plus the other leg is 7. We square that, and that equals our hypotenuse, which is 14. We're going to square that as well. Let's simplify what we can. T squared plus, well, the 7 squared is equal to 49. And 14 squared, that's one I'm hoping you guys had memorized, but if not, you're free to use your calculator there, is 196. We're going to subtract the 49 from both sides. Those will cancel. And that's going to get us now t squared is equal to, and a 196 minus 49 is going to get us 147. Kind of an ugly number over there on the side. All right, and we would undo this square by doing a square root on the left and a square root on the right. The square and the square root cancel out, so we get t equals, and now bad news bears, everybody, 147 is not a perfect square. So what are we going to do? We're going to go 147 divided by 2 in our calculators. That was 73.5. That obviously is not a perfect square because it's a decimal. So start thinking about perfect squares smaller than 73.5. Okay? All right, so 64 is the first one we see there. So 147 divided by 64, nope, not going to work. Keep going down the list. 147 divided by 49, that's the next smallest perfect square. Hey, and that one worked out. It's 3. So the 147 now becomes 49 times 3. Okay, we split it up. This is now the square root of 49 multiplied by the square root of 3, and we simplify what we can. The square root of 49 is 7, and you can't do a darn thing with the square root of 3, so 7 root 3 is your value of t. All right, everybody, we're going to wrap up part 2 of these notes, but I've got one more coming for you here pretty soon on how to use the Pythagorean theorem kind of backwards to classify triangles.